Let's begin to talk about elements of the thermal balance of our planet, beginning with solar radiation. Just a few facts and figures. The amount of energy emitted by the sun is spectacular, about 4 times 10 to the 26 joules per second, which if one divides by the surface area at the top of the photosphere, one arrives at the figure of about 65 million watts per meter squared. Now, if we take into account that the average distance of the Earth from the sun is about 150 billion meters, this tells us that the flux density of solar radiation at the mean radius of the Earth, which is just its luminosity divided by the area of the sphere, is about 1,370 watts per meter squared. We call that the solar constant. Now, as we'll see later in the course, it isn't exactly constant. It does fluctuate a little bit with time, but in small parts of 1%. Now, if we did not have an atmosphere, it would be fairly easy to calculate the surface temperature of the Earth from something called the Stefan-Boltzmann equation. This simply says that a perfect emitter, called a black body, emits radiation over all wavelengths at a rate proportional to the 4th power of the temperature times a constant called the Stefan-Boltzmann constant. Now, if we look at what this implies about the temperature at the top of the sun's photosphere, given that the radiant energy emitted from the sun is about 65 million watts per meter squared, if we simply use the Stefan-Boltzmann equation to estimate the effective emission temperature at the top of the photosphere, we get an effective emission temperature of about 6,000 degrees Kelvin. What happens to that solar radiation? Well, we can first calculate how much of it is actually absorbed by our planet. So we're going to take the solar constant, which remember is the flux of solar radiation per unit area at the top of the atmosphere, and we're going to multiply it by this factor 1 minus a sub p. A sub p is the planetary albedo. It's the fraction of incident sunlight that's reflected by the planet. We'll later see that that's highly variable across the planet, but it averages about 30% or 0.3. So the total absorbed radiation is just the solar constant times 1 minus the albedo times the amount of radiation intercepted by the disk of the Earth, which is just pi, times the radius of the planet, r sub p squared. So the total surface area of the sphere is 4 pi r sub p squared. And that means that the amount of radiation absorbed per unit surface area of the planet is the solar constant divided by 4 times 1 minus the planetary albedo. Now, the absorption is accomplished mostly by the surface, by some gases in the atmosphere, and by clouds and aerosols within it. What happens to that radiation once it's absorbed? Well, ultimately, since the planet is in energy balance, the amount of radiation it absorbs from the sun must be balanced by the emission of radiation to space. Let's make a rough estimate of the effective temperature at which the Earth radiates to space. We can do that by using the Stefan-Boltzmann equation to equate the total amount of energy emitted by the planet, that's just the Stefan-Boltzmann constant, times, we'll call this the effective emission temperature raised to the 4th power, and set that equal to the amount of radiation absorbed from the sun, the solar constant divided by 4 times 1 minus the planetary albedo. That would give an effective emission temperature of our planet of 255 degrees Kelvin, or minus 18 degrees centigrade. This is approximately the mean temperature the surface of the planet would have if we did not have an atmosphere. And of course, it's much lower than the observed average surface temperature, which is closer to about 288 Kelvin or 15 degrees C. In the next video, we'll talk about why the observed surface temperature of our planet is so much larger than would be predicted by this simple equation between emission and absorption of radiation.